Alright, so the last little piece to molecular bonding is VSEPR theory. And VSEPR theory only applies to molecular compounds. It only applies to nonmetals and nonmetals. And what this says is that we can predict the shape of a molecule based on lone pairs and ligands. Lone pairs are going to be unbonded. Pairs of electrons on the central atom. Okay, that's a lone pair, LP. Ligands are bonded pairs of electrons on the central atom. So lone pairs and ligands, and you need your VSEPR theory chart, which is on the purple sheet that's laminated, or you can Google VSEPR theory chart and you should get some responses that you could use. So ligands are in the first column, those are bonded, lone pairs are in the second column. So I'm going to go back to our examples here so that we can just determine the shape of these. So H2O has 2 ligands, 2 lone pairs. 2 ligands, 2 lone pairs is bent. CCl4 has 4 ligands, 0 lone pairs. 4 bonds on the central atom, 0 lone pairs. 4 ligands, 0 lone pairs, tetrahedral. CHF, 4 ligands on the central atom, 0 lone pairs, again, tetrahedral. CO, double and triple bonds count as 1 ligand. So 1 ligand, 2 ligands, 0 lone pairs is linear. 1 ligand, 1 ligand. Okay, double and triple bonds count as 1 ligand. And anytime you have a diatomic or just two elements, it's automatically going to be linear. And that's VSEPR theory. It's very simple. You just count lone pairs and ligands. And you're counting them based on the central atom. All right. Ionics. Dot structure of ionics are a little bit different because we're going to draw the dot structure for each individual element. Then consider what has to happen to the electrons to make an octet. And then we draw the dot structure for each element after it has completed its octet at the products. So for example, magnesium oxide. Magnesium has 2 valence electrons. It's in group 2. Oxygen has 6. 2, 4, 6. Now we write these like chemical reactions. So magnesium needs to give 2 of its electrons to oxygen. The reason that magnesium gives up its electrons is because it's easier to give 2 than gain 6. It's easier to give away $2 than to get somebody to give you 6. So magnesium gives up 2 valence electrons, giving it a +2 charge. Oxygen gains 2 electrons, giving it a -2 charge. This is what I expect to see for a dot structure for an ionic compound. The starting elements with the valence electrons, arrow, and then the elements after they've given up their electrons plus their charges. So I'm going to do one more. NaF. Na has 1 valence electron. F has 7. So sodium is going to give up 1 valence electron. Meaning that sodium now has a +1 charge. Fluorine has a -1 charge. I'll do aluminum oxide too, just because it's different. It's got subscripts. So aluminum has 3 valence electrons. Oxygen has 6. So how many valence electrons can aluminum give oxygen? Well, it can give it 2. Oxygen's happy, aluminum's not happy, it has an extra electron. So I need another oxygen to give this electron to. But now, that oxygen's not happy, so I need another aluminum. Okay, aluminum has 2 more to give away, so I need a third oxygen. So if you count Al2O3, this is why we crisscross charges. Because this tells us how many aluminums I need for how many oxygens. I need 2 aluminums to satisfy 3 oxygens. So just to clean this up a little bit, Al3 plus oxygen 6 yields Al plus a full octet oxygen. Al with a +3 charge, oxygen with a -2 charge. Now, you could balance this if you wanted to, but I'm not going to require you to balance it. I just need you to be able to write the chemical reactions. How do I know when to do a dot structure like we did with molecular or this? Well, this is if I have a metal. Metal, you do the reaction. Non-metal, you don't do the reaction. You just do the dot structure.